New images captured by the James Webb Space Telescope have astounded experts. Instead of expanding our understanding of the universe, these images revealed a troubling truth. Our current physical models are inadequate to explain the nature of the universe in its earliest stages. As the Big Bang theory reaches its limits, scientists are now forced to consider alternative hypotheses about the universe's origin. This raises the question: how exactly did the universe form? And why do these new discoveries challenge even the most experienced astronomers to rethink the Big Bang and the finer details of its evolution? To understand the significance of these findings, we must revisit the Big Bang theory. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Instead, space itself began to expand roughly 13.8 billion years ago, alongside matter and time, from a singularity, a point in physics where gravity is so intense that spacetime becomes infinite. Today, after billions of years since the universe's beginning, we observe that our cosmic home is part of an ongoing cycle. For scientists, this suggests an inherent property of the universe since its inception: an apparently endless expansion. However, it's important to understand that the universe isn't expanding into pre-existing space. Rather, space itself is expanding. According to conventional models, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was the point when the first bright celestial objects began to clump together to form mature galaxies. But how quickly these galaxies formed remains a perplexing mystery. A significant clue emerged from the James Webb Space Telescope's first images, released in July 2022. Scientists announced that the telescope had detected several galaxies that existed as early as 300 million years after the universe's creation. However, compared to the galaxies that formed billions of years later, these early galaxies were significantly smaller and less massive. This finding fits well with the scientific model that suggests the matter density in the young universe was insufficient to create galaxies as large as those observed today. What began as the discovery of 6 distant redshifted light sources by the James Webb Space Telescope quickly escalated into one of the most significant galactic mysteries of recent times. Although these newly discovered galaxies are similar in age to previously detected ones, they are nearly as large as our own Milky Way galaxy, a finding that challenges established cosmic theories. After analyzing a series of images captured by Webb's near-infrared camera, researchers identified these newly discovered light sources using redshift. They concluded that the light from these objects took more than 1 billion years to reach us on Earth, meaning these galaxies had already existed about 5,700 million years after the supposed Big Bang. By examining the characteristics of these galaxies, it was determined that Webb had captured 6 very early galaxies. These galaxies were so massive that they defied expectations for cosmic evolution. Rather than the small, faint galaxies typically predicted, Webb detected galaxies that were nearly as large as the Milky Way, despite having formed early in the universe's history. If this data is correct, it would suggest that these galaxies contained more than 10 billion solar masses at the time, with some possibly surpassing the 10 billion solar mass mark. This observation raises several significant questions. Even if we accept this possibility, it would imply that there was far more stellar mass in the early universe than previously believed, presenting a major puzzle. These objects contradict nearly every conventional cosmological theory. Even if just one of these galaxies is confirmed to be real, it would force us to rethink our assumptions about the early universe. Moreover, the matter density in the early universe would have had to be far higher, multiple times greater than previously assumed, to account for such large structures forming so early. Another intriguing explanation suggests that these galaxies formed in ways that remain completely unknown to us. This recent discovery and the ongoing debates about the Big Bang are prompting more researchers to question the validity of the Big Bang theory itself. Many astronomers are now proposing alternative hypotheses, though these views are often dismissed as speculative by the mainstream scientific community. Even those who defend the Big Bang theory are facing difficult questions without clear answers. Some of the most pressing questions include how and why, 13.8 billion years ago, something seemingly emerged from nothing. Could something really come from nothing, or was there a triggering event? Or was it all just a coincidence? Steven Weinberg pointed out that the concept of time as we know it began only with the Big Bang, making it impossible for this process to have been initiated by anything external to it. Furthermore, scientists observe a remarkable uniformity in radiation and matter density throughout the universe. No matter where or how far we look, we find similar distributions of galaxies, nebulae, and radiation. This phenomenon is often explained by the theory of cosmic inflation. Some researchers take this further by proposing the theory of chaotic inflation, which suggests that inflation may have ended in certain regions, like bubbles, but continues indefinitely in others. This implies that multiple universes could exist within these bubbles, each with its own physical laws. Under this model, our universe may simply be one part of a much larger multiverse structure, where the Big Bang is just a part of a broader cycle of collapse and rebirth. In this context, the Big Bang theory would no longer be the ultimate explanation, but rather part of an ongoing cycle of universes. This model proposes that the universe could be eternally collapsing and regenerating, leading to an endless process of rebirth. Yet, this is just one of many views emerging in cosmology. In addition to the Big Bang, alternative theories have been explored, such as the hypothesis of an ancient cosmic explosion suggested in a 1955 article in NASA's Astronomical Times. As scientists continue to analyze the data from the James Webb Space Telescope, the mysteries surrounding the universe's origin and its earliest stages are only deepening. The answers to these questions may challenge not only our current understanding of cosmology but also the very foundations of space and time itself. The concept of dark matter and dark energy, two subtle components that account for most of the universe's mass and energy content, continues to intrigue scientists. While dark matter is thought to provide the gravitational framework crucial for the evolution of galaxies and the universe, its distribution and properties in the early universe remain uncertain. In light of these astrophysical mysteries, theoretical physicists are exploring alternative models of cosmology that challenge the traditional Big Bang theory. Some theories propose that our universe is just one of many within a vast multiverse, each governed by its own unique set of physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, suggest a more complex and interconnected universe than previously imagined. One such theory is that of eternal inflation, which posits that new universes continually emerge from an ever-expanding space. In this view, our universe could simply be one bubble among countless others, each with its own distinct properties. The main challenge is finding observational evidence to support such speculative ideas, as they push the limits of experimental verification. Another provocative theory suggests that our universe might exist within a simulated reality, similar to a computer-generated recreation. This idea draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with astonishing accuracy. If this were true, our perception of reality as a physical universe could be profoundly altered, raising significant philosophical and scientific questions about the nature of existence itself. Meanwhile, advancements in observational astronomy, particularly through instruments like the James Webb Space Telescope, promise to unveil even more of the universe's secrets. With its unprecedented sensitivity and resolution, the James Webb Telescope has the potential to shed light on the earliest moments of the universe and offer clues about its ultimate fate, as well as the fundamental laws that govern its development. Beyond observational cosmology, particle physicists are investigating the fundamental particles and forces that shape the universe. One of the central goals of theoretical physics is to unify gravity with the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Theories such as quantum gravity and string theory offer possible frameworks for understanding these interactions at both the smallest and largest scales. In the realm of quantum mechanics, the very nature of time remains a subject of intense debate. The traditional view of time as a linear progression from past to future is challenged by quantum theories suggesting that time might be emergent, or even illusory at the fundamental level. Understanding the nature of time within the context of cosmological models could revolutionize our understanding of the universe's origins and evolution. The search for extraterrestrial life also continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope study of exoplanet atmospheres, may provide evidence of biosignatures, offering clues to the existence of life beyond Earth. In addition to these scientific pursuits, philosophical and social reflections on the universe shape our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration continue to stimulate thought and debate across disciplines. As we stand on the brink of a new era in astronomy and cosmology, fueled by technological advances and theoretical breakthroughs, we are reminded of the profound interconnectedness of all things, from the smallest subatomic particles to the vastest cosmic structures spanning billions of light-years. The universe continues to reveal its mysteries to those willing to explore and question. Ultimately, the study of the universe and its origins is an endeavor that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. Discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe, raising new questions about its formation and evolution. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic expansion, we move closer to a more complete understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a journey to decode the vast and intricate puzzle of the universe. Whether exploring the depths of black holes, tracing the paths of distant galaxies, or probing the very nature of existence, each new discovery brings us closer to unraveling the complex tapestry of the cosmos. As we venture further into space, guided by curiosity and driven by a desire to comprehend the universe's vastness and intricacy, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, a never-ending journey of discovery, wonder, and enlightenment that continues to inspire generations of scientists and thinkers alike. In the words of Albert Einstein, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." As we confront the universe's greatest mysteries, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of both the cosmos and ourselves. The exploration of the universe is not only a scientific endeavor but also a profound human quest for knowledge and meaning. It is a journey that transcends the confines of space and time, encouraging us to reflect on our place in the grand tapestry of existence. One intriguing perspective suggests that the universe may not have experienced a singular, massive explosion. According to this view, the universe could have existed for an infinite amount of time, with no true beginning, and the continuous formation of matter could give the illusion of ongoing expansion. In this context, the universe would not have a definite origin or explosive event, but rather a steady, ongoing development. An alternative, thought-provoking hypothesis comes from the realm of quantum physics and string theory. Some studies propose that our universe, and everything within it, may not be what we perceive it to be. In simple terms, the observable universe could be a three-dimensional hologram projected onto a higher-dimensional surface. This theory suggests that we might be living within a simulation created by an advanced civilization. Though this may sound like something out of a science fiction movie, it connects to the Kardashev scale, which measures a civilization's technological advancement based on its ability to harness energy. A Type 3 civilization, capable of tapping into the energy of an entire universe, could potentially create such a simulation. However, confirming this reality is an incredibly complex challenge, and exploring these ideas brings us into the mysterious and ongoing realm of cosmological research. The recent images captured by the James Webb Space Telescope have reignited discussions about the fundamental nature of our reality, prompting scientists to reconsider established theories and reconsider key aspects of cosmological understanding. Central to this exploration is the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, the universe began approximately 13.8 billion years ago, emerging from an incredibly hot and dense state, expanding rapidly and giving rise to space, time, and matter as we know them. This massive event is not merely a big bang within pre-existing space, but rather the actual birth of space itself. The idea of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, underpins our understanding of this early universe. However, the recent discovery of ancient galaxies by the James Webb Telescope challenges assumptions about how quickly structures began to form in the early universe. These galaxies, detected within just a few 100 million years after the Big Bang, appear far more developed and massive than expected based on current cosmological models. One of the major questions raised by these discoveries concerns the concept of cosmic inflation. According to the dominant theory, inflation occurred in a fraction of a second after the Big Bang, causing the universe to expand exponentially. This rapid expansion explains the uniformity of the cosmic microwave background radiation observed across the universe today. However, the recent findings suggest that the early universe's development may have been far more complex, requiring possible revisions to the inflationary models. The formation of galaxies, such as those observed by the James Webb Telescope, pushes astronomers to reassess the conditions and processes that govern the universe's early history. These galaxies, which are significant in size and mass shortly after the Big Bang, imply a matter density that exceeds previous estimates. This presents a profound mystery. How could such large and complex structures form so rapidly? The discovery of these early galaxies further raises fascinating questions about the origins and evolution of the universe.